Okay, so this is our last week in this semester. So next week is for a final exam. So we don't have a final exam. So this is the last week for our semester. But we have a homework, our last homework, which due next week. 好，所以我们这一周最后有一个最后一次作业，就是作业5。So in today's lecture, we are going to talk about the first we're talking about homework 5, and then we are going to do to cover a topics about Llama Omni, which is a speech language model. We have already talked about some of the multimodal model, but most of them are VLM. That is combining vision ability to the large language model. And we also cover a little bit about how can we generate image with large language models. Although in principle or in theory, doing the speech or audio are quite similar to the to aiding the ability of to aiding visual ability to the large language model, but in technical details they are quite different because audios has a very high frequency for like a image. Probably you have a resolution like 1000 by 1000, but for an audio it is typically that it has a frequency like 22,000 hertz. That means it vibrates like 22,000 per second. So every second it has a resolution like 22,000, which is very very large comparing to an image, because usually you will have like 10 seconds or maybe like 30 seconds speech to make it usable. So they have different challenge to the audio encoding with large language model. 所以我们第二个会讲的是那个 speech， 就是语音的。虽然前面有讲到那个视觉语言模型，原理上就很接近，就是编码然后喂给那个语言模型，但是在技术细节上面它是不一样的，因为语言有语言的一个生态系，它的频率很高，很常见就是 16kHz， 就是16千赫或者是22千赫，也就是说1秒钟它就解析度就是22千就是2万多或者是1万多。那视觉模型可能就是1000乘1000的图片，所以它有一些特性是不一样的。当然它也是有点像是编码，但是它编码方式不一样。And then we are talking about some of the acceleration method for large language model and the diffusion model. We're using Ego3. We're looking into the Ego3 paper to discuss what is speculative sampling, and using the TCatch paper to explain about the catching mechanism. What is a catching mechanism doing to kind of cheating and speed up the model? And finally, we are going to discuss about the 3-dimensional sense. We're covering nerve, 3D Gaussian splatting, and finally text to 3D. We probably will skip nerve or 3D Gaussian splatting a little bit if we don't have enough time. But if we do have time, we still want to talk about these two topics, although they are not generally considered to be as a generative model, but in some loose definition, they can be considered as generative model as well. And also some of the generative models, like text to 3D models, some of them are using like 3D Gaussian splatting or like NERF as a representation of the 3D object. Although not all of the text to 3D model use these two techniques. We probably have a quick summary about the things we were covering in this semester to kind of refresh your memory. And also mention, okay, I probably should mention right here, it's a good time. We haven't covered anything about the generative adversary networks, which is quite contrary to like previous years. So even in last year, we covered generative adversary networks for like 3 weeks, or maybe even like 4 weeks, which is still significant portion of the whole whole lectures in the semester, but we didn't cover it at all in this semester. We covered a little bit about we talked a little bit about the matrix and evaluation, which was, I put this part into the sections of the GAN part, the generative adversary network part. Although I still think the GAN works like I have always said, GAN will fade out the importance. I mean, like 5 years ago, GAN is super important as what the diffusion models as today. But back then, I would say that one day, which is foreseeable, that the importance of the GAN will reduce and replaced by other models, perhaps by flow models, which was quite promising back then. I mean, before I even knew that diffusion model exists, diffusion model exists for quite a long time, but I know it a little bit before the paper, diffusion model based GAN. So I know it quite late, like 2020 or so. But even before I know the diffusion model exists, we know that GAN has some drawback and weakness, and it is likely there will be other techniques that can replace the importance of the GAN. So I was thinking that because flow things, I mean the flow models are quite promising. So it might be some sort of variation of flow model or new theory about doing the flow model, and perhaps similar to like the neural ODE, because we'll probably have a homework doing that using a neural ODE to, or probably not, I forgot. But in previous, we will have a homework that using a neural ODE to run the flow model. So I was imagining something like this. So the prediction was not exactly correct. So it is a diffusion model, but diffusion model is kind of similar to the flow model. And currently, the flow matching model are used, and it is strongly related to the flow model. And although technically they are different, but they have came from the similar ideas, and they are using. I mean, one of the root of the diffusion model is a stochastic differential equation sense. So they're still using. People are still kind of sometimes using the ideas from differential equation and using some tools from differential equation to act like accelerating the process of sampling, or sort of or draw some idea or intuition from some mathematical theory to create a new algorithm or new variation of diffusion models. Okay, I'm just saying that the reason that one of the reasons that we didn't cover GAN is that it is mostly replaced by diffusion model. So the importance is objectively kind of decreased a lot. But also, what I was saying is that even though I was predicting, I was thinking, or always know that GAN will be replaced by other algorithms. In the same time, I was always saying that GAN will still has its position, because GAN is a method that to define a loss function without actually knowing what the loss function is. So basically, GAN is using a neural network to define a loss function, but kind of like the LPIPs. LPIPs use a pre-trained model as a loss function. So this kind of things is still useful, sort of like the FID that we mentioned in the matrix. So you can use a pre-trained neural network and use some of its layer and use other loss function apply on these layers to become your loss function. So that is doable. But in the GAN case, the neural network is not pre-trained. It is trained along with the generator itself. So that's the idea. So this kind of paradigm or idea still works. It falls into a thing, I mean, a routine that if something that is very difficult to define or to modeling, then you use a neural network to do the job, to do the work. So in a whole process of your work or your workflow or your research, most of probably can be easily defined or I mean formulated in mathematics, but some of the part is very difficult to use to define more like informal or in mathematics. So you just replace that part, you identify which part is difficult to formulate, and you replace that part with a neural network. That is a general solution to a lot of different things. Including, in some sense, including the 3D Gaussian splatting or like NERP, which we're talking about later in this lecture. So GAN is also fall into the same category because the idea is that it is difficult to define loss function to check the similarity between two distribution or two image. So that is difficult because it is difficult to explain, to determine which image is more like a real image or someone is better, someone is worse. It is difficult to do that. So we just replace that part and train a neural network to do so. That's pretty much the idea. So that pattern or that idea is still useful when it applies. It's just we have different tools. So in the case of image generation, it is not as popular as before because we have alternative solution like diffusion models or like variation autoencoder, the advance of variation autoencoder. So the drawback of the GAN or why the GAN loss is because the diffusion model is more scalable. GAN is pretty effective, but it is require a lot of tweaks and tuning over hyperparameters or architectures if we have a larger data set. So that is the only fault of the GAN. It is not that the GAN itself, in principle, have some weakness or some unfixable issues. It's not like that. It's just nowadays we have tons of large data, so it is quite it requires a lot of effort to tuning or tweaking the hyperparameter or models to make the model training works. And it is kind of tedious because we are adding more and more data. I mean, when we try to experiment, okay, which data is better, which data is not that good, we need a lot of experiment. So if every time I have to adjust the model hyperparameter, it's very tedious and will be very slow. And besides, even though even if other alternative is not so efficient, it's not as efficient as GAN training, maybe I mean suppose we have this case, it's not a problem because large companies has a lot of GPUs. They can parallelization the whole task to do it in multiple machines. So that speed itself is not a issue, but scalability is an issue. So that's why the GAN does not work. But if someday people figures out, if someone figures out how to scale up the GAN, although it is not likely because it is kind of, because we have to train two models that has exactly opposite target or goal, so it is kind of unstable by nature. But if someone figures out some way to make it more scalable, so maybe the GAN will rise again and replace the diffusion model. Maybe that is possible, but chances are the problem you are going to solve can benefit from GAN. So this is still one of the tool in your toolbox, as always. So it will never, I mean, outdated or like totally useless. It is still one of the tool in your toolbox. It's just not as important as like 5 or 10 years ago, 5, 7, 8 years ago. Okay, so we still have materials in previous years, but I didn't cover it or discuss in this semester. So you can still check this material, like 2024 material, and check the video recording in previous semester. Okay, so let's go to the homework. So this homework is, I will not say easy, but it's more relaxed homework the task is ask you to generate a video using open models. I'm not saying open source models, but at least they release their weights so that you can use them. The consideration of homework, one of the consideration and quite bottleneck consideration about the homework designing is always computational power. We are unable to provide everyone enough GPU computation power. So every time I consider these works, I will have to consider that we are not going to use too many computational power. So although I think fine-tuning a video model is more challenging and more useful and meaningful, but that requires, I've tried in low computational power machines. When I say low computational power machine, I mean some machines with a GPU like 8 GB, or not a machine with only CPU, but I think it is still reasonable. I mean, at least you can use Colab. There has a T4 for free. So although it is a little bit slower, so I'm consider something like a T4 GPU on Colab, or like small consumer, like a mid-range consumer GPU, maybe a 3060, like a 3060. I think it has 6 GB RAM, VRAM, or maybe you have a better one like or older one like 2080, or maybe better one 3080 or 4090. I was thinking something like that, but 4090 is. I was thinking about something that much slower, or like has little smaller memory size comparing to 4090. I'm thinking about something like I said, like 8 GB VRAM. So, but that is not very practical and requires a lot of time. And if you didn't do it correct in the first time, it probably will you was. I mean, the training is probably like 1 or 2 days. So if you fail, you have to do it for another 1 or 2 days. And even though if you have a computational power, it probably used in other projects. So I'm thinking about something that with less computational power requirement. So this is one of the things that I think is still useful and meaningful, but you don't need to have a very powerful machine. So that is generate a video using open models. But you don't need to worry about, okay, I have tried to host video generation models on my machine, but I don't have enough VRAM. There are some open models that require only a little bit VRAM, like 6 GB VRAM can already run some of the video models. But the thing is that you can use Hugging Face space, and I have tried at least one workflow, a pipeline that can work with this homework. There are multiple ways to do that. So first, let's see what is the assignment or target of our homework. We are going to ask you to generate a video, kind of like this one. I'm showing you this video right now. Okay, so you are seeing a man working, but while he's working, every 2 seconds, he's changing his outfit or maybe his appearance. You can change anything, or background, even the background. So you are going to create a video kind of like this one. A person is working or doing something, but for every 2 seconds, it changed to another thing. But the person is still I mean, when the scenario or people change, the person still remains the same position. I mean, same position and the same pose, and continue his movement. The background, even if the background change, it looks similar. Like, so for the first change, it only changed the outfit, but for the second one, the third one, and the background is changes a little bit. So you are doing similar things like the one. So I'm going to explain how you will do it. So you can, if you prefer that only the outfit is going to change and remain the background, it is doable. Probably requires a little bit of effort and a try, but it's doable. Originally, I want to do a few clean outfit change, but I do it in a really quick and harsh time. So I didn't do it in a perfect way. So you can definitely, if you spend some time like 4 hours, you can definitely do a much better quality video. Okay, and also I have constrained myself to using only Hugging Face services for free. So I didn't use any. I have a Comfy UI hosted and can run more advanced models by myself, but I didn't use them. So I didn't use any I will talk about it, but I didn't use any like the face or function control models for video generation. So I didn't use any more advanced control condition video generator. I'm just using the ones that available on Hugging Face Space。好，所以这个东西设计上其实重点是，还有这个东西其实没有升得很好，原因是因为我现在局限在只用到 Hugging Face Space 上面的服务。哦，那如果你有电脑可以用，可以自己装一些的话，那它会弄得更好。好，那如果有更多一点点时间的话，其实也可以做到更好，但是大致上要做一个像这样子的。So let me talk about the requirements. Although I was thinking about the requirements of the resolution, but I kind of given it with, you can do it with any resolution because of the same reason that people may have memory limited. You don't have enough video memory, so even if you have a smaller VRAM and you want to do it locally, you can do it with a lower resolution. Okay, so the requirements require you to use local model, open models. So because considering that people may not have a GPU, so you can either use a self-hosted models if possible to actually run a video generating model on your machine. Maybe you in your lab's machine or in your own like laptop or PC. But alternatively, you can also use the models hosted on Hugging Face Spaces, so which we'll talk about some of them. And the video should combine multiple generated clips into one single video. The final video should consist of at least 4 segments, each lasting 2 seconds. And their transition should be like what we described or you see in this video. So the official requirement is similar to this one or better than this one. There are some explanations, but the whole purpose of this homework is kind of give you a start point to familiar with open tools that are available on the internet. So if you are already familiar with all these tools, then that's fine. You can use any tools available and any models available to your knowledge and use their full potential to create something amazing. That's fine, but you have to kind of combine 4 segments together, at least 4 segments. If you want to do it longer, this one is probably like 10 seconds. If you want to do a 30-second things, that's fine. That's fine. Or if you want to, one of the segments is longer than 2 seconds, then that is also fine. I'm not having a frame rate limitation. This one is probably like 25 frames per second. So if you want to do a 10 frame per second, that is fine. But the reason that we don't have a frame rate requirement is because also again, considering people may not have enough video RAM, so I don't want to give a requirement of frame rate. But so in principle, you can do 1 frame per second if you really want to do that, but probably you shouldn't do that. You just use a video model to generate things, because this one is already a quite doable things if you just following this workflow. In fact, I'm expecting you can use a better way to generate a better video, but because this one is not, the first transition is okay, but the third one I accidentally changed the background, and the third and the fourth one, it is intentionally changing the background and the face, but you can see that for the last transition, the movement is not smooth. You can see that this guy kind of stall a little bit, then start working. So it is not in a smooth and working movement. 所以这边的问题其实就是就是它其实这个东西其实做的没有很好，因为它很多问题啊。因为刚才已经讲了，所以我再讲一遍。所以第一个还好，就是第一个跟我讲的一样，就是他直接换衣服，然后背景也没有太大的改变。但第二个的时候，这个背景不是我想要改的，我可能有一些没有做好，但是因为就很快做的比较快啦，因为只是要出作业的时候做比较快一点点，所以这个东西没有做很好。最好是只有换衣服。好，那第三个这个东西是预期的，就是我希望它背景变，人也变，因为这个是用不同方法去做的。但是他的动作其实有点变慢了。好，第四个就是你看他开始的时候稍微，当然变得更多了，但是他开始的稍微停了顿一下，这是我不想要的。那如果我有后面有一些，就是我如果多试几次，或者是我用比较好的方法，它其实可以避免掉这些问题。So I can actually avoid these issues by using alternative methods. Or I can, if I try a few more times, I can pick a better one to fix these issues. Okay, so the requirement is kind of like very loose, and there are a lot of loopholes you can find, but please just doing something that is similar to this one and better than this one. Okay, there are various ways to achieve this. So I'm giving you one of the pipeline that is workable and doesn't require you to host anything on your own machine. You can only use Hugging-based things. So first, you need to have a starting frame that is like this one at the very beginning. You can generate any, you can actually generate a segment of videos, like 2-second videos, by using any video generator, text to video generator. Or you can generate the first frame like this one suggests. Okay, so this is one of the generator, the flux, one depth. So you can, okay, just a mass working. Then it will generate using a diffusion, using a flux to generate a first frame of a man is walking. You may want it working on a city. But this one seems pretty well. So you can use this one as the first frame. That is one way to do that. Then, okay, or you can use local image generator instead. Or even, I'm not saying even better, but you could also generate directly by using any video generators. I'm using another one. Let me use 1.2.1 fast. Okay, which you will see in. So this one is a man is walking. Okay. Then you can use text to video generation, or you can upload the image you just generated. It is not. Okay, maybe I can use this one. Okay, so maybe I can So let me generate a video. So by the way, this one is using a close-fit LoRa on 2.1. I2V means image to video, and the 2.1 is one of the we probably have already introduced it before. It's one of the SOTA open source open video generating models. It currently has a like 1.3B version and the 14B version. Okay, so you have the first one here. Then it's working. Close-fitted is also another way to accelerating to speed up the video generation model. Also, close-fit. So it's related to our topic of speed up diffusion model, speed up generative models. So close-fit is a LoRa to apply on 2.1. I mean, a fine-tuning method to apply on 2.1. It kind of like LCM or like fast video things to make it can run in like in general we have to sampling it like 25 steps, but here the inference steps is only using 4 because we are using a close-fit technique to do that. So it requires fine-tuning, kind of like LCM and fast video. And here you can adjust the durance of the video. Like here is 2 seconds, which is a very reasonable time for current generation. Longer time requires longer time. But anyway, this one seems to be okay. And then okay, alternative for the first segment, you can also download a free image for the first frame. You can even download video from them, but you can only use only like 2 seconds for one segment. You still need other 4 segments to like generated images, generated videos. There are Pixels is one of the sites that I use. I'm not subscribing to it, but this is one site that I get public domain, free public domain, or Creative Commons 0 image or videos. If so suppose you are making videos, maybe you're going to publish it on YouTube also, you need some material that you can content that you use to like a transition or like illustration, or even if you want to use it on your slides, your PowerPoint. Here is a way to legally find like materials that you can use without assets that you can use without any copyright issue, because they are all public domain. So you can check. So you don't have to trust me. You can check his legal license and legal. So all photos and are free to use, and attribution is not required, because if you are using some Creative Commons, not Creative Commons 0, but Creative Commons license image or video, you will have to contribute to the original creator. It is not only polite, it is required by the copyright laws. So you have to contribute, like putting a text saying who is the author of this image or things. Although it still have something that forbid to do that, but these things are kind of common sense, like they are truly illegal. Like identified people may not appear in a bad light or in a way that is offensive. You do not offensive in the people in the image or things like, or like sell these things because they are free, and if you sell them in other things like make profit, it is not used. So it is not legal or allowed to do that. But if you are just trying to make your own videos, they are totally free and legal to do that. So it contains a lot of things like, for example, if I want like jumping, I'm not using walking. If I'm using jumping, I can get something like this one. So this one, maybe you can use this one as your baseline video. So if you want to use a more advanced pipeline, like face or like uni-animate or like kind of like control net things for video. If you want to use control net things for video, like you use a pause to do that, you can use this video as a reference. So you can generate a longer video and it will have a smooth motion. So anyway, let's go back to our poor man's workflow. Okay, so first you can generate your first piece of segment, clip, video clip like this one. And then you will take the last frame to as a start point of this one. So I'm not doing it right now, but you can use FFmpeg to do that. FFmpeg, you can install it in Anaconda environment, or if you are using Linux or you are using Homebrew, like in Mac OS, they can be installed pretty easily. So for Windows, if you are using Windows and you are not using Anaconda, you just want to have a Windows thing, there is a version for Windows, but yeah, you can use other tools as well. But FFmpeg is, if you are going to do a lot of video things or doing simple video process for research, for study, for like workflow pipeline, FFmpeg is a Swiss knife for a lot of things. It can resize the video, can change the aspect ratio, can clip, can padding, can combine two videos together. One thing to do that is to actually extract the frames from a video to like a sequence of images. Also use FFmpeg. If you don't know how to use it, to frankly speaking, that FFmpeg, the argument of command line argument for FFmpeg is not exactly the most easy thing to learn. For me, I didn't learn it very well. However, we have ChatGPT, we have Gemini, we have Cloud, we have a lot of AI. So nowadays, it is not an issue. You just ask this AI assistant to tell what you want to do. Like, I want to combine these two video together. I want to resize this video. I want to do certain thing. ChatGPT will tell you how to do that. So FFmpeg is more recommended more than ever because we have the AI assistant. So you can use FFmpeg to like combine this video to clip together. If they have different resolution or different frame rate, you can also use FFmpeg to fix them. Also, you can use FFmpeg. If you really have the issue to use FFmpeg, you can use other video editing tools to combine this video together. But it will be, I mean, I use Premiere Pro a lot. We have a subscription discount, so I use Premiere Pro a lot, and I use like other things like OpenShot, video editor for like one of the free software popular choice for video editing. And there are other things like more advanced, but I use OpenShot a lot. So you can also use them as well. But I highly recommend that you can try the FFmpeg because it is a Swiss knife for doing a lot of things. You can do that in like 1 or 2 seconds. And you can just, when you want to do the similar things, you just in a command line environment and use up arrow to find the previous command and change it a little bit, then you are done. So it is quite fast and efficient way to do that. However, I'm not going to use FFmpeg right now because I only share my browser windows, so it will require me to do a lot of different things. But I'm going to demonstrate how to use this one. Like I'm changing the cross of the first frame. So for the first frame here, let me try the virtual try-on. Virtual try-on means try different clothes, different outfit. The virtual try-on means you give an image and change the outfit of the person in the image. Google just announced in Google I/O announced their service. Virtual try-on has always been a interesting topics and a lot of research on it. So I'm just choosing one that seems to be trending right now. If you have, I mean, the Google try-on I think it is already available, but I'm not sure it is available only on the subscriber or like in United States, because a lot of service of Google, they are saying that, okay, they are available today, but what do they mean? Available today for people in the United States. Also, because it is always as that, because especially like in Europe, they have a very protective to human, people's rights and privacy. So always you will see that a lot of service of Google or other big company does not available or will available a lot later than other areas in Europe. So maybe they are available to Taiwan, but they are not available to Europe because of the laws or other things. Let me pick up the image right here. So for example, I can change his clothes to this guy, which I use in the video as well. So again, I simply click wrong here. It will do the job for me. And you can see that here is 39 seconds, which suggests, okay, you are expecting it will run like 40 seconds or 39.5 seconds. In fact, it is saying that last time it runs this job for 39.5 seconds. So it is not very accurate estimation because image have different resolution. But anyway, I got this one. So you use this one as the first frame of the second segment of video. But I'm using the first frame, not the last frame of the video. So I cannot use it directly. But still, let me just download this one and pretend it is the last frame. So then I go to maybe here and change this one to this one. Okay, then I generate the video again. So I will get the second video clip, and I use FFmpeg to combine them together. So that is the first transition. So you think that if you're doing everything correctly, the background will remain the same, and the main only change is outfit. Although you have to be very careful because the resolution may be changed, so it may cause you some issues. But you can specify the resolution of the generating videos right here to make everything just work. So you can see that this one is the second video clip. So if the movement is in a different path, you can perhaps you can do that you have a prompt right here. You can say, okay, in a slow pace, okay. Let me do it in a very slow pace, slow motion, or maybe you can use this one. Hopefully this one will help you to have more control on this image. I mean on the video generation. You can see that the video generation is pretty fast using coarse video, and the quality is not too shabby. I'm not entirely sure it is slower than previous generation, but I'll take that it is not fast at all. Maybe I'm doing it again, like you can try it like working it at a very fast pace or fast speed. So you can try it out, and it's very fast without any much cost. So as you can try that. Okay. Other than first try on, maybe you can use like control net union or other control net things to do that. Or if you think you should want to only change your background, you can use a background remover. Okay, there are a lot of different control net space in Hugging Face. Let me use the pretty old control net 1.1 or SD3 control net. Okay, let me use a control net SD3. I haven't used it before. Let me try this one. Okay. Okay. I'm not sure in which control net it is using, but okay, he's using Kenny. You can use depth, Kenny, or pulse, or anything, but he's using Kenny. So let me write this one. Let me change it to a woman. Okay. Let's just see how well it works. I haven't tried it before. My personal favorite is using the depth. Okay, so it becomes this one. So you can see that it remains similar because Kenny is an edge detector. So the edge or the shape remains similar. The color is not because it doesn't have a color. Okay, you can see that this one is the condition. This one is we call this one reference image, and this one is condition. It's condition, and this one is a generated one. So you can see that definitely generated, or maybe I can see that. I always spell it wrong. Okay. So here's another astronaut. Okay, you can also become this one. This one seems more dramatic and more impact on visually impact. So maybe you can try things like this one and kind of a man working and like in different timeline, different situation. So again about the terminology, let me use this one. This one is the one I used to create the sample video. So the terminology is that you can see that this one is called the process control image, which is conditioned sense. So if you have already doing the process by yourself, like Kenny, like depth map or other things like here, soft edge or Kenny or depth or open pose. If you have done the things, you can put the process image right here. So although here says optional, but you can see here it is a reference image. So you should put the image right here, like this one, right here. So the prompt is also like okay. Let me try. Okay, we use Kenny right here. I like it. Okay, good. So let's use Kenny as a fair comparison. But you can also use depth. I use depth or open pose as well. But okay, depth. So I mean, Kenny is also very popular, and you can kind of keep the shape of the things. But it requires more time. So let's check it back later. But I think the previous one, the SD3 control seems to be quite well. So you can also use that. Alternatively, you can use background removal or any other models available to do the process like image conditioned generation. Okay, so you repeat this process. So once we got alternated or adjust image, we can use it as start frame to create your second video clip to make it working. You may add something like the man is in the middle of the view, or in the camera is following the man, to make sure the people is not going. I mean, what asking these people to walking, right? It may walk out of the camera and disappear. This is not something we wish to have. So you can add something in the text prompt to make sure the man, our main character, is still in the middle of our video. So you can add something like that to make sure, and you can try 4 different video clips and combine them together. So that's one way to do that. And here is a hint that you can use MPEG and how to use them. So the above pipeline can be done by using Hugging Face space alone only. Maybe I should say that only, without using any self-hosting models. If you have a machine that you can run local models, maybe you have H100, like 80 gigabytes memory, or even better, or maybe you have something slightly worse, like you have a 40 gigabytes video memory. Then that's fine. Here are some suggestions, that tools, if you haven't heard it before. Let's first check how it will. Okay, it actually follows the prompt quite well to control a chimpanzee walking in a forest. So you can do something like this one. Okay, so one of the so here is also a small list of current available popular tools for video generation. Although you can also use like Field 3, Field 2 or Field 3 on Gemini, or like Sora on used by using ChatGPT. It is totally fine, but not they are not allowed in this homework, because the purpose of this homework is to familiar with open source or open models. So here is a list of open models that I think is quite it is not a complete list, but covers some tools that is quite enough to help you to do this homework. So first one is the Convey UI, and although Convey UI support one video natively, it supports 问源 one. One is 万象 in Chinese. and LTX video, and still video diffusion, and maybe matrix video one in natively. But because a lot of people working on this like a custom node, like a plugin, this one is not official, but the ecosystem is quite good, so you can still check this one. And besides, it provides a lot of different models that it can be that is used in I mean a lot of different models in the one video ecosystem. I will probably not call it an ecosystem, but there are a lot of fine-tuning, modification, customization around original one video models. It is still not in a scale like the community or like ecosystem of the Flux or like Stable Diffusion, but it is still a community that is quite active. It's quite active. So it contains a lot of models that in the one community, like Phantom. Phantom is a model based on one, but you can combine several different elements out to the video. We will introduce it in previous slides. Phantom, when we talk about the one community, we have talked about Phantom already. And the UniAnimate is a pose conditioned video model, so that you can actually control the pose of the main character in your video. Font control is also like a control net. So it can use a depth, canny. I forgot other things, but at least it can use depth and canny to control the video. And it also have impending, which is called the font impending. They didn't use the forward like a function. I think the font is function, not for font. But I'm not entirely sure about it because they are using a short and things. And imp means pretty much is impending because this is what it does. And ACC video is acceleration, kind of like cost video. So it is called ACC VID. It is an acceleration on video generation for text to video generating. And the cost video is also like we say that it is a acceleration on the video generation. Uni 3C control net. I haven't seen this before, and this is uploaded like 5 hours ago. So this one is a new thing I haven't known it before because, but by the name suggests it might be a control net thing. So we probably will try it. You can probably try it. I haven't heard it before. It must be a new thing. And you can again, you can see an ACC video. The difference between this one and this one is a LoRa, and this one is a full model. And one video also has a first frame and the last frame to video, so you can control the start and the end altogether. So you can extend the video in both ways, like in previous things or in the. You can use a reference image as the first frame or last frame or both. So that is quite convenient and very controllable. This is a control font control weight, like also like similar to control net, but it doesn't have a control net like we said before. Also, it has image to video. Movie gen is a fine tune of the one that generate more cinematic, like kind of like a movie vibe of things. Then cost video is acceleration things, text to video, different text to video, and the face is like image and video to video things. So it can also serve like a control net and also has a start. I mean, kind of like a font control, but you can try the fast or font control. They have different qualities, things. So you can use it as a animate or a font control, but it has a little bit more functionalities, also different. This one is kind of changing the camera things, and fantastic talking. I haven't used it, but it seems like can make the person talking in the video. So if you want to, like you see in the sample video, we don't have um, we don't have audio with the video. Okay, so this one is something you can do. Here are other model like the text encoder things. This one I don't know what it is. Okay, so although this one is like uploaded 2 months ago, but I haven't actually looked into it. I'm not looks like a text autoencoder for one, but I'm not entirely sure what it is. Okay, so here is the Comfy UI, and also the original Face has more options. Like not only it can work for like one, it also works for like LTX video as well. And here is font control sense. You can see more detail on it. And one original 2.1, you can see the whole community update, like Phantom we mentioned before, UniAnimate, SafeG0, Tcache, and DiffSense Studio. And also Skyreels V1 is a model that focusing on generating people. It is based on Hunyuan. You can, if you want to use it and prefer to use it, it is still a pretty good choice. And also, Skyreels A2 is kind of like a Phantom. You can put like several components and to control your videos, so it is more handy. Although I'm not entirely sure what you can do with this homework, but maybe you can generate the first segment of video, and then start from here. And the Hunyuan video is still very, although I mean people are using one and thinking one can generate more high quality video, but Hunyuan is still very active and can generate things. Okay, so and also the fast video also support Hunyuan. Okay, so sorry, allow me to. Okay, so for this homework, you should submit your work, your generated video. So it is very short clip, so it should not be very large, and describe the things that you use in this describe the tools that you are using. Like for first clip you are using, you don't have to mention about the FM pack, but you have to mention which models you were using and on this kind of things. So okay, So the details will be on the E3. But basically, you have to submit the video itself and let us know which of the models that you were using. Okay, so this is the homework. Now, for the second part, let's talk about the speech model. There are many different speech models, but a lot of them are quite similar. Basically, you may think it is difficult to train or kind of like a magical to do that, but kind of like the image, visual language model. A lot of them are kind of just grew up that combine the existing models like large language models and existing like text to speech or speech to text model. Of a popular speech to text model is Whisper, and there are many speech. I mean, if you want to transcribe or like converting things, audios or speech to text, Whisper is one of the popular and obvious choice. And there are a lot of models to generate speech from text. Some of them are kind of zero-shot models that can mimic any person's voice. Like you can just by like 10 seconds or 20-second audio clips, then you can use that person's voice to say anything you want. Okay, so let's see firstly the llama only. So I mean, the obvious choice is just glue them together, and you know how to glue them up because you can use a projection layer to adapter, just train adapter to translate one latent space to another. So that's the typical idea for doing so. So let's talk about the llama omni. Llama omni is also pretty similar to what I was described. 所以llama omni 跟我刚才讲的差不多，就是它就基本上就是把 whisper 跟一个 text to speech 粘在 llama 上面，差不多就是这样做而已。So it kind of just grew up, I mean, combine the whisper and text to speech model with the llama. But one of the characteristic or the special point about it is it simultaneously generate a sense, I mean, a speech and a text altogether. So the benefit of this is that the training data can contain like any pair of things, like speech to speech, speech to text, text to speech, text to text. So you can have a pretty variety and differences in your data set. So that's one of the special points about the llama omni. Okay, so let's see the different part. I mean, perhaps we should see the architecture first, then we see the details. So it has speech encoder as well. I read this paper like 4-5 weeks. I don't know. It has been so my memory is a little bit fade, but if I remember correctly, the speech encoder is just whisper. It takes some layer of the whisper. Of course, there's a speech adapter you need to train, but here it's just whisper, and you need an adapter to become large language model compatible tokens. And then when doing the output, it has of course it can generate text and audio at the same time. So this one is audio. It has a speech decoder, and also it has a vocoder. This one is very typical, and you will see that this vocoder is a pre-trained one, although they didn't use a off-shelf vocoder they trained by themselves, but this one is a pre-trained one, and you have a speech decoder which is trained with the language model. So it has the training has two stages. So the first stage, it only trains the language model and the text-to-speech part. You can see that it trained the speech adapter. It has a speech adapter. I mean, the other way around, it only trained the speech understanding part. So it trained the speech adapter and the large language model. Kind of like the Blip 3.0 we see before. It's training in the first stage, it's training the image understanding. And this one is training for the speech understanding. And the speech encoder is fixed. And you only train the adapter and the language model itself. And for a second stage, it fixes everything. It only trains the speech decoder. Because the vocoder, which we were saying why we need a vocoder. But you can see the vocoder is a common practice in text-to-speech. In more classical models, they use male spectrum. But in recent years, people are using neural network things. But before that, they're using, more like a latent thing. But here, in the like 5 years ago, the vocoder is a thing that can decode a spectrum into wave. But right now, the vocoder is decoding a latent into wave. You will see that. But anyway, the only thing need to be trained is the speech decoder, kind of like a adapter from this guy to in the vocoder latent. So it also has two stages. Although the vocoder in this paper, they have trained their own vocoder, so it can actually can speak in multiple different voice. I mean, it has a multiple speaker in this same vocoder. They have a speaker identity, if I remember correctly, because there are a lot of similar models doing the similar things. But for the Omni, I think they have multiple speaker ability. Okay, so let's see in the detail. Let me check if it has other. Okay. So the following are some like data set or things. We are not going to cover them. But if you are interested on the data set, how they control data set, you can check them. I'm more focusing on the components to describe what the components here. Okay, so first of all, the speech encoder, it is whisper large V3. And it uses certain latent to representation. So so it is using a whisper as a encoder. And then it uses a speech adapter, which, as we see before, it is trainable in the first stage. So it adapts the latent, the representation in the whisper to align with the large language model. So this is a speech adapter. But basically, it's kind of like the image understanding model. They usually have an image encoder like a VIT or mask autoencoder or anything can encoding the image into some representation. Then they use an adapter to translate them to align with the language model. Also, this one is for the input or understanding. And for the large language model, they use Llama 3.18b instruct as the base model. Okay, for the speech decoder, did they? Okay, let's see. For a speech decoder, they discretize the speech into discrete units. Okay, so they are using Hubert. Hubert is the a model that can extract continuous representation of speech and then convert it into a discrete cluster. So it's kind of like a VQVAE, You get a continuous things and then you translate it into a continuous data, and then you make it into like tokens. A lot of previous approach use the same latent space for output and input, but in the Llama Omni, you can see that for input they use Whisper, and for output they use Hubert. Although both of them are quite popular, but a lot of previous approach use the same representation space for the input and output. So that is also a spatial part of, the characteristic or like the things that you can notice on Llama Omni. Other than that, everything looks similar. They have a speech encoder and adapter, and for output, they have put some text-to-speech system and have adapter on it, although it's called the decoder. So the space of output things they call Hubert. So it is a discrete sequence of things. So they can translate them like a large language model because they have the things like that. And for the output, they use hi-fi GAN vocoder. Okay, so they are using a vocoder that called hi-fi GAN. The hi-fi GAN use similar discrete unit sequence as their like latent or things. Also, this is also a vocoder. So comparing to like a more traditional classical things, the vocoder translate the male GAN. They are vocoder like a male GAN. Something like that in like text-to-speech things like 5 years ago. It is a vocoder things that can translate a spectrum. Spectrum 就是频谱啊，有一种频谱特别频叫 male spectrum. So they translate a spectrum space, which in particular popular is the male spectrum space, into wave like real audio that you can play on your like player. But recently, a lot of things that, especially on the large language model, they are using Hubert space and using hi-fi GAN is really popular. Hi-fi GAN vocoder is quite popular. Also, you can check the hi-fi GAN paper to see what it is. So you can see like TTS hi-fi GAN here, vocoder. It has a lot of different vocoder, and basically, it should be, the vocoder itself, because it is not only, it also contains the speaker's personality or characteristic. So I have some doubt for its use for the multi-speaker, but apparently some people can use it vocoder, to kind of change the vocoder to make it output different voices by simply changing given a parameter to the vocoder. But anyway, so they use hi-fi GAN vocoder, and they generate a speech response modality with text response. Okay, so that's pretty much about it. If you're interested in this part, you can read this paper, because the data set preparation, the process is also interesting. For example, they are using some text-to-speech, because a lot of data sets are only in text. They have only text data, like text input and text response. So one issue is that, okay, we don't have an audio response. So maybe we can use a text-to-speech model. They probably, I think I remember they use a different text-to-speech model to generate the audios, speech audios from the text. So they can serve as input and output. And because for the input, they need to be more, has more variations. So they are choosing one that can generate like a speaker, the same thing using different speaker ID. And another difference is that even though if you have a text output, and you can use use a text to speech to convert this text to a speech, but in general, these text response are usually too long for like a speech response. When we write something as a response, we can allow it to be quite long because we can skip the reading and to find out the part we need. And sometimes it even have some like markdown table or like the list things. It will become very annoying if it becomes a voice response, because you are going to listen to a very long things and not exactly relevant to your response. So usually the speech response will be shorter and more get to the point, and sometimes in a different format than a text response. So you cannot just simply convert your response from text to like speech audio, even though it can be done by using a very good, using a decent speech, text to speech models. So you still need to rephrase this response. So they are using another language model to rephrase these things into something more concise response that is more suitable for a speech response. So that is quite interesting part for the rest of the things. To be honest, I kind of mix up a few paper about the speech language model. So this one, I may kind of mistaken some materials from other papers to this one. But that is generally something that speech language model would do, like to construct a data set. So if you are interested, you can read the following and or check other speech models. Okay, they of course they do that speech synthesis right here, and they have some details about how they do that. Okay, so let's go back to here. Okay, so that is a briefly discussion about the audio speech interaction with large language model things, because we mostly focusing on image or video generation or multimodal model with about the visual representations and like language representations. We usually focus on that, and so we slightly mention about how the speech would work with large language model. And of course, there's also a model that some model can work with visual understanding and speech understanding, feature generation, speech understanding. along with the language capability. So there's some model about that. You will see that quite often, and it will become the standard in one, I would say in 1 year, because the time, the things kind of very change very fast. I was thinking about like 1 to 3 years, but I think I can pretty confident that you will see a lot of truly multimodal model in the following years. Okay, next, let's talk about the acceleration. As you can see that the video models generation is quite fast. Like what do we see? Like although we only generate 2-second videos, but the generation is kind of like no longer than 1 minute, right? Maybe we can check here. We don't get the time here, so let's just generate it again to see what happened. So this one time does not count because they are waiting. So let's just see, okay, how long it takes. Or like less than 1 minute, about 1 minute. So although the speed can still be improved, but I mean, ControlNet generate the things is taking longer, right? The ControlNet, we have a ControlNet. It took longer to use the ControlNet, but here it only had like 53 seconds to generate. It's not too bad. Okay, so acceleration for the video or image generation is a thing, and a lot of work has done for it. So let's see how some methods are used to speed up the language model generation. So one of them is the speculative sampling, and Ego3 is one of them. So let's first see what is speculative generation. So you can see it is a speed up method, can apply to any other any pre-trained language model. So let's see how it compares to others. So for example, Ego3 can have a 5.58 speed up compared to original one, and maybe up to like 7.54. So it is a huge speed up. So how does it do it? It does it by prediction. Let's see this figure. Okay. Okay, so let me check something right here. OK， 好，我们从这边开始。这个图可能比较好一点。OK, so let's see this one. So suppose we are starting from this sequence. How can and we want to generate file things in a typical autoregressive manner. We'll generate the second thing based on this. Like, how can I do? How can I help? How can I do? How can I do? Then after we generate a do, we generate it. So we generate a token one by one. How can I do it? Maybe a question mark. How can I do it efficiently without any dangerous? Something like that, but you generate the token one by one. As you can see in Olama, it will show you two speeds. One is the speed for handling or processing the prompt, and the other speed, like token per second, is for like generating response. Let me check it. For example, for image. Okay, so this one might be a typical one. I'm not sure I can see the image. Okay, so for example, this is a prompt evaluation rate. So they are handling running the key cache things for the prompt. It can speed as fast as 200, more than 200 tokens per second. But for like doing the response, it can only do like 82 tokens per second. So it is like 2 or more speed up. In some cases, it is even the difference is even bigger. This one is not that huge. Let me check some. Maybe we can see some. My personal experience is a larger differences. So this one is larger. This one is for the prompt evaluation, it is 33, and for like here it is like 10. So it is more than 3 times speed up. In some scenario, it will have like 10 times speed up comparing the prompt evaluation and for the generating the response. So why is there such a difference? It is because when we try to do the, so first of all, when you try to generate the response, it will have a longer context compared to the prompt. But also, the major difference is because when you do the process the tokens in parallel, it will speed up things, especially if you have a huge machine. I mean, you have 8 GPUs, or like even if you have only 1 GPU, GPU is very good at doing things simultaneously. So if you do things simultaneously all at once, it will speed up. And you have some mechanism to like optimize the caching mechanism or other things to speed up things. You have a room to speed up. If you have to generate one token by one token, there's no more room and it is less efficient. So the basic idea is that if we can generate a bunch of tokens at once, it will have, I mean, the throughput is much higher than generate it one by one. So that's the idea. So can we generate, I mean, how can I do it more efficiently? Can we generate do it efficiently at once? I mean, in typical situation, we cannot, because before we generate, we are unable to generate. But how about, I mean, we can guess what we would generate. I mean, for like speculative sampling, the idea is we use a smaller model, a faster model, to guess what we are going to generate, because sometimes we are going to guess it correctly.所以 speculative sampling 它的 idea 就是，因为你东西同时生的时候比较快，那我们又必须要先有前面才能生后面，那不如我们就先猜猜看嘛，猜中就猜中，猜错也没有太大的损失。So the idea of speculative sampling is that, okay, we use a faster model to guess what will come next. And maybe we're not going to guess correctly every time, but if we have a decent accuracy, like maybe like 90% of correctness, so 90% of the time, if I can guess this correctly, I can speed up this one because we can generate them all together like 90% of the time. For the 10% of the time, yes, we are wasting some time to do the guessing, but it is not that bad. It will slow it down a little bit, like we have 10% more time. But when we speed up, we are like 2 or 3 times or even faster speed up. So that would be pretty good deal. That would be a pretty good deal. So some like 90% time we can have a 2 times speed up, and for 10% time we have a 10% penalty. So that seems to be quite good deal. So we can, so that's the idea. But we will have to have a model that had 90% accuracy, or at least pretty high accuracy of guessing what is going to be next. So that's the idea of speed up. So of course, you can imagine there are many different variations. First of all, what is the faster small model? So we call it a draft model. 我们把它称为是草稿模型 draft model. The draft model is supposed to be smaller and faster. If I mean, suppose you are trying to speed up a Llama like 70B model, you are not using another Llama 70B model as your draft model, because it is as slow as the original one. There's no point to use. I mean, if the draft model is as slow as the main model, then you use the draft model, or you use the main model. You don't use both. So the draft model must be faster, much faster than the main model, but still keep a high accuracy of guessing correct next token. Okay, so obviously you have a choice of draft model. So a apparent solution is, okay, if we want to speed up Llama 70B, we use like Llama 7B as the draft model. So apparently Llama 7B is much faster than Llama 70B. So we use Llama 7B, or maybe we have a Llama 3B to generate like the next 10 tokens. And we use these tokens and use a mask to ask the Llama 70B to generate the next 8 tokens at once. So it will speed up the process. If we are guessing like the first one or second one, or maybe many of them correctly, then we'll have a speed up. So that's the obvious choice. But the smaller model is not exactly, may not have, I mean, compatible with the large model, because the small may still generate a valid response, but they may choose different way to express them. So the accuracy may not be that good. So one obvious solution is to distill a large model into a smaller one. So that's another choice. So another choice is, okay, since the large model, I mean, although it haven't done to generate the next token yet, it's still done a lot of calculation. Can we use this calculation to speed up our smaller model? And because we're using the computation inside the large model, so the small model will have a better chance to align with the large model. So that may be increasing our accuracy of prediction. 好，所以另外一个路线就是，我们可不可以用那个大模型已经计算过，因为它中间算很多层嘛，它已经计算过的内容，当做辅助来帮助我们小模型去节省预算时间，因为这边已经算完了嘛，就重复算了嘛。那而且呢，它至少知道大模型在想什么，那这样就可以预测更好。So this is the idea of ego. Okay, so we're talking about ego 3, but let's talk about ego first. So this one is ego. So instead of predict a token directly, the draft model taken some intermediate output, mostly like the logics of the model, or like some intermediate output of some intermediate model, some intermediate output of a large model, as the input, and they are going to predict the next output. And this output can go to the language model head to generate the correct output. So these guys are corresponded to the output. So we have already seen it when we discuss the detail in GPT-2. So for example, these are just factors, and we are using cosine similarity comparing to the embedding of the model, and to find the most similar one, to use that as output. Or we compute the cosine similarity and use this similarity to pass through a softmax function to get the probability of the next token. So these one are not the output of the probability or the next token. They are simply some intermediate output in the model. But we can use this one and LN head to get the actual token. So for ego, when training, because we are using a data set like the fine-tuning, supervised fine-tuning method, so we can get a next token. We can get a next token. Because we can run the data set on the large model. So we can get the intermediate representation right here. The feature, we call it the feature. So in the ego, it has two loss. One is the feature loss, and one is the token loss. So this is ego when training. But in the training, it only train the next token, because this is how the language model could train. It can only train, the autoregressive model can train. It only can train the prediction of next model. For the second next token, because we're not entirely sure what is the input of the next token. We have what is the ground truth for next token. We can do that. But for the second next token, because we don't have the actual output of the next feature, so we cannot train it in the more apparent way. Okay, so anyway, the ego has two loss function. One is the feature loss and one is token. So because the feature also has a loss, so this feature and the actual feature, the ground truth feature is the feature that generated by the large language model. They are not going to be so different, because we are using a feature loss like a mean square error to align the output of the draft model, in the sense of feature, to the large model. So the feature is also very close to a large language model. So if we forget about token, this is also a sequence-to-sequence model, autoregressive sequence-to-sequence model. So this one kind of training works and can align with the large language model with high accuracy. So when we do the testing, although we haven't trained it to predict the next the second next or the third next token, because the feature are aligned, it can do pretty well on test time. And by their experiment in the ego, it can have a pretty good result on benchmarks. However, in the era of large data set and in reinforcement learning, the ego does not perform that well. So they investigate and they find out that the bottleneck, or the thing that to get things to prevent them to get a better result in the benchmark, is this loss, the feature loss, because it is a more constraint than they original consider or imagine. It is a very large constraint. So the obvious way is to remove this feature. So by removing this feature, they can get a pretty good prediction on the next token. But for the second next token or so on, they are not very good because the feature is not aligned with the large model, although the token is aligned, but the input and output are features. So the first output, the feature is not close to the feature of the large model. The feature output by the drive, predicted by the drive model is not close or similar to the output, the actual output of a large model. Although the first token is the same, but the first feature is not similar. I mean, they still have a pretty good accuracy on the first token because they still have a loss on the token. But this is not so true for a second next token. So they need to change their we have talked this on the autoregressive models. It causes some kind of sampling bias or like the bias. That is the train time and test time. The difference between train time and testing time. Okay, so this situation is similar. So they have to find a way to overcome this issue. So the thing is that, okay, so instead of feeding the drive model with the ground truth feature, we are feeding it with the actual, I mean, the feature that generated by the drive model. So, and we have to train it to predict the next token. So in this way, although the training method seems to be a little bit complicated and expensive, we're talking about detail later, but this one seems to be working. Okay, so how do they actually do that? Okay, so this one is a training sense. So this one is a prompt, how can I? So they are doing the typical autoregressive things to generate like, we do things. So because we're training an autoregressive model because we want to make it efficiently and get most of it. So when we are not only predicting the next token, we're pretending it to be like 3 sequences. The first sequence is how, and the second sequence is how can, and the third sequence is how can I. So we can train these 3 things simultaneously. So for we use the mask to do so. So everything can be do very efficiently in one pass. So in the first pass, we do the typical autoregressive things. We generate how are, how can we, and how can I do on the 3 next token. And we are combining these 3 token, next token, into our training to do to predict the second next token. So it's kind of like a 3 things. So in these 3 things, we have 3 new sentences, 3 new sequence. The first sequence is how are, and the second is we, how can we, and the next one is how can I do. So in the second phase, we are using these 3 sentences to predict the second next token. Okay, so we do the same thing with this one and predict the like how are you, how can we help, how can I do it. Okay, and we can do it again for the third next token. So this one is the mask, and we do the third text, the third next token, and so on. Of course, it is kind of slow and expensive, but you can still do it in kind of like for a similar benefit of like training an autoregressive model. because you can predict. You can handling like in this case, 3 sequences at once. And because we are going to mimic, predict the output of the large language model. So unlike the case that in autoregressive model, we don't have a data set. In this case, we have a data set because the response can be controlled and generated by a large language model. So we know we have a way to get what is the next token. So we can get the true next token as well. So this one is doable, although it is still kind of, you can imagine this one is still kind of slow, because every time you have to, I mean, if you want to have more depth, like more tokens to in your training phase, it has to run kind of like a loop. For one batch of data, you have to have like a loop to run it like 3, 4, 5 training. So it should have a limitation on how deep it should go. So in fact, the depth, typical depth is like 6 to 8 in Eagle 3. In Eagle 2 setting, it's like 6. The depth is 6. I remember. Oh, that, yeah, the depth is 6, and they are not going to predict only one result, because we know sometimes we have multiple choice. So it is more like a tree kind of things, and this is doable because we have mask. By using the mask technique, we can do the tree things at once. So in order to increase the chance of prediction, sometimes we have a branch of prediction. Like how can I, how can you, how can we, or maybe these 3 are all equally possible. So maybe we will branch right here. So they have an algorithm to select which branch they are going to choose. And totally, they have a totally number of draft token, like 60, 50, or 48 draft token. So give it a higher chance to guess things correctly. Also, this one is equal to 3. So to be in detail, it has a detail in the architecture, like how it concatenates the features from the large model and combine with embedding. And this one is phase 2 to get to the next token, and they get the second next one, and so on. Also, the model, the draft model itself is pretty small and simple. It just get many features from the large language model and combine it with the actual embedding. So each of token actually combines a lot of memories of the tokens from here. And this one can be relatively smaller. Okay, so this is the way that to speed up by using selective sampling. Another popular way is like a linear transformer. It changes the formula of the transformer into another things, which can be much faster. So that's another way to do that. Another way to do similar things is called a T-catch. Similar catch mechanism also can work for the large language model, but this one is for, especially for like diffusion model, for like video model or image generative models. This one is called a T-catch. The basic idea is that a lot of computation in diffusion model, as well in language model as well, so that they can, why this can apply, is a lot of the works computation are redundant. So in the diffusion model, we have a lot of different steps for sampling. not everyone is actually doing a lot of significant change. So in language model, similarly, we have a lot of transformer block. Some of the transformer block is not doing much of work, but the situation is different in diffusion. So TCACHE does not apply to language model, but the similar idea is they have a lot of computation, but not all the computation is necessary. So the idea is to identify the computation that is not necessary, so we can skip that computation. Because when we identify things that the input and the output are similar or almost no change. It is also observed that in large language model, because large language model are usually designed in like a residue net. They have a lot of residue block. The residue block is only compute the residue. I mean, the major part of a neural network only compute the residue. So a lot of them are very similar to the identity function. So the input and output are the same. So in the diffusion denoising process, sometimes the diffusion denoising things, the noise of this level are pretty similar to the noise in the last step. So because noise is kind of like the momentum or speed, it pretty much says that, okay, sometimes we can use the momentum or the speed in the noise in the last step and apply on this one. So it will has a constant denoising process. Kind of skip this step. So they use an algorithm to do that, to kind of predict whether or not this step is going to change a lot. If not, we don't compute the noise. We don't predict the noise. We use the noise predict in last step instead. So how this is possible? The thing is that they find out the input of the input difference is, I mean, the output is very correlated to the input. So this one is the identity things, and this one is the input difference, and this one is the output difference. So they can use the input to predict the output. So they observe, they didn't train any model, they use an algorithm to observe the input and to predict whether or not we should run the denoise step again on this step. So also, if we have already skipped a lot of steps already, and we can calculate the total difference between this step. If this difference accumulated difference is large enough, then probably we should work. So it is a smart way to skip works, kind of a smart way of being lazy. We probably should not saying lazy, because lazy has a very specific meaning in computational context. So it just skips things. It may not be lazy, because lazy means we are doing it when necessary. Although this is also kind of like doing the denoising when necessary, but not exactly the same idea. So I'm just saying it skips steps in a more smart way. The algorithm they are using is using a very simple model. That is a polynomial regression, to kind of slightly align this data with the straight line. That's it. That's it. So that is called a TCACHE. So you may surprise it is so simple, but it is. I mean, in the practical using. People are reporting. I mean, people reporting. I'm not saying that in the paper. I'm saying that in Reddit, a lot of people share their workflow and their experience. So a lot of people saying that they didn't observe any difference when the threshold, let threshold saying when should we update. When for a suitable threshold, people are reporting, are saying that, okay, we didn't observe any the quality loss, but we can have a reasonable scale up. Okay, so although the algorithm is not that groundbreaking things, it is applied on, they have actively applied these things on different models, perhaps by community. So like FramePack support TKH, Fast Video supports, Easy Animate support, Rui model supports, Consistent ID support, and in Conv UI, like it has a TKH node you can supply in general, but like one video and like Hunyuan, like a lot of also support the TKH. So you can pretty much expect to speed up any popular model by using TKH. So here is a list of supported models right here. Although in the paper they are using Open Sora, they probably only apply it and do a benchmark on Open Sora, but so they can do it. They are pretty much in practical. They are support pretty much every model as well. Also, this is another way to identify, another way to speed up the inference, but identify some of the part that is not is redundant. You can skip that. You can skip. So in large language model, a lot of people are studying. Okay, can we? There are some constants diffusion, like we have a 70 billion parameter model, which is huge. Can we remove some of the layer so that we don't reduce the quality of generated text that much? You can actually remove some of the bug, and it will not immediately become something that totally useless. The quality will definitely goes down pretty significantly, but because they are using residual blocks, so even if some middle blocks or one of, because it has a lot of different blocks, you just randomly remove one of the blocks, probably in the middle part. Chances are it will still respond some reasonable response, perhaps not as good as the original one, but it will not just simply respond like garbage of things. 好，所以其实大语言模型有类似的现象，你随便把一个 block 移走，如果一个够多 block， 你随便中间移走一个 block， 它大致上还可以运作，因为它大部分都是用 residual 的方式，所以不会差那么多，不会差那么多。所以如果你随便移一个的话，它很有可能，不是一定都会，但是很有可能你移走一个，它还是可以 output 上一些还可以看的一些文字，只是在一些 benchmark 会明显下降。Okay, finally, let's talk about 3D. The first thing we want to talk about is NERF. It's called the neural radiance field for field synthesis. The idea is pretty simple and straightforward. We use neural network to record things. So what is neural radiance field? Basically, what it does is you can video. This one is not for original paper. This one is following up work like instant nerve from NVIDIA, but it pretty much says how it works. So first you take photos from different angle. Like in this case, a woman is taking holding a camera. So we take several pictures in different angle. And then you will reconstruct a 3D models that you can view it from different angles and in very detail. Okay. So how does it does? So basically, this is not that surprise because it has been like, I think it has been 15 to 20 years. We already have something like multiple cameras and has interpolation. So like, okay, maybe more than 20 years because in the movie Matrix, if you remember in the like this one or this one, it has a 360 wrong field when at the stop motion. So these similar things, because they have a lot of camera on 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 a 330 degree around these things, so they can replay it like the time has been stopped, and from different angle to see the things. So this kind of things already has and already has used similar technique has been already used in like sports event. In maybe we don't. I mean, if you think this is only done by a huge number of camera, it is not, because it still has to use some algorithm to do the interpolations between one camera to another. So for like a sport event, you may say that in like 10 years ago or 20 years ago, it already has ability to sometimes to have a 360 kind of round view of things. It can be any angle. So in a small, I mean, a sports live event, it may have like 4 cameras or like 8 cameras. They have been in a very long range to camera inside the sporting field, and although it only have 4 or like maybe 8 cameras, by using some algorithm to do some interpolations, it can make you have a view of the like a 360-degree smooth rotation to view the object. So it has been done by using algorithm already. But in that setting, you have already know the camera position, and you can only do the rotation because you can only do the interpolation from one camera to another by using certain interpolation algorithm. And also, the quality is not as, I mean, it is only an approximation. Although, because it is rotating in a very smooth and fast speed, so it is not that observable, but it would have some blind spot and some like geometry incorrectness on the things. So I mean, I'm just saying it is not perfect. Although there you can use some computer vision algorithm to like do inpainting, to do things, but first of all, that is already doable. Secondly, there are some. So I mean, by using nerve, it is not that surprise, but it definitely improvement. So what is it improve? What is the improvement? So first of all, they can have a camera at different position. So the idea is that we do the camera position estimation. So this is done separately, and this technique already has been developed before nerve, because there are already a lot of 3D construction things. So the nerve can use this to do the estimation. However, nerve is actually using a neural network to do the interpolation. The interesting part is that it is not using a pre-trained model to do the interpolation. It is training a model by using this data to do interpolation. So by given some position like X, Y, Z, your camera's position and direction as input parameters, and we're training on the given data. We are training it on given data. We can do interpolation and also some certain extent of the exploration, because this is a neural network. No matter what input you give it, it will give you some output. So the idea of nerve is, okay, we are using X, Y, Z and the direction we are seeing. And we are using the existing input image as a training data. So you can see that optimize the nerve. And we have a neural network. We are training it on this data. Then from any position and any direction, we can actually pass an output. And hopefully the neural network will work. If our training works well, we can get a very smooth and more reliable, or maybe I should not say reliable, or more the fidelity is better, a better fidelity view of this 3D object in any direction. And also, this neural network is combined, like you don't need to do the implanting separately or do like adjustment or things separately. You can use one neural network to solve everything. It becomes like you convert the original problem into a data set and a training problem. And that's all. And you can see that the input is 5-dimensional things. It is the X, Y, Z, the position of the camera, and the direction. Okay, so this is a neural radiance representation of the things, like the photon density and the field-dependent color. This one is the things that you get from any point. So they are having a 100 input views of a synthetic drum randomly captured by surrounding hemisphere, and they can have another view of these things. But basically, it is just interpolation. So this is a continuous 5D function, X, Y, Z, theta. This is the direction. It's more like at this point, it is emit color and light from there. So they have a RGB color from different direction. So that's a basic idea of neural nerve. And it can have a pretty amazing result, although it is, if you think about it, it is not that surprising. And you probably kind of already know it is going to kind of work even before it is beginning. But still, the result is quite impressive and has a very huge impact. And people are going to, has been studied and improve it in many different ways. Like 4D things, like 4D means not just the 3D object, it also has a time on it. So what if we only have a video input, like surrounding it, but the object is moving, like a human, he's walking or dancing. Can we also use this as well? Obviously, this is a more difficult problem. You can imagine that it does not, if you're doing it in a vanilla way, it does not work that well. But you can also think about a lot of variation or improvement on this algorithm to improve the result. So there are a lot of work about the 3D nerve. One of the, I'm not entirely sure it is still the best one. In fact, I'm pretty sure it is not. But back then, it is one of popular tools by NVIDIA that can do the instant neural graphics pretty fast. I'm not sure it has been updated, and there are new tools about 3D reconstruction. You can find a lot of them. But another significant, like I said, there are a lot of improvement, like making it faster and apply better quality and apply on different things. But one of the fundamental change and milestone improvement is 3D Gaussian splatting. So instead of the original neural radiant field representation, it uses a Gaussian splatting instead. So the result is quite well, like in details. They're choosing like the bicycle, and they can see the wheels here. You can see more details. Basically, they are using a Gaussian splatting. As the name suggests, the Gaussian splatting is not considered a point, and the color, the light it emits, it consider the object as a bunch of small ball. When I say ball, I mean we could have a different radius in like x, y, z direction. So it's more like a elliptic ball, which is because like a Gaussian distribution in three-dimensional space. So it is more like a Gaussian distribution, or like you can think of it as a kind of blurry balls in a space. So the representation is more like this one. So by using this representation instead, it can the experience says it has better qualities of things. So it also runs the optimization on the training data, on the observing data as well. So here is a repo for like 3D splatting, Gaussian splatting for the original paper. And here is that something you can actually get to do the camera estimation. The Gaussian splatting and neural radius field, the training time is actually quite fast because it is just training a relatively small neural network. So the training process is relatively fast. However, if you want to calibrate all the cameras from the photos you get, it is tedious and long, expensive work. Typically, you can use CoreMap to do that, which is a standard tools to do the camera calibration or camera position estimation. So this can be considered as a pre-process if you have a bunch of images that are taken from. So it will give you the positions of these cameras and for each photos that cameras at. But there are also like CoreMap-free 3D Gaussian splatting available to make everything. You don't need to run the CoreMap separately. You can do it without a CoreMap. So there are a lot of things that can really speed up the construction, the reconstruction, or the training. not train, not the reconstruction process. So here is like a CT Gaussian splatting. So you can see that it can do a very large scale rendering with Gaussian splatting, even with a CT. So I think this type of technology is getting popular recently. You can find a lot of tools and open source tools, or maybe like apps to do that in a really large scale. Although neural nerve since has already been for a while, but I think the quality and the scale is improved a lot, because for like a CT scale scanning and reconstruction, by using similar technique, is quite difficult back like 2019 or 2020, like 5 years ago. But right now, I think a lot of software can do that, and in a very short time. I haven't touched this since for like a while, but like one year or two. So I'm not catching up the ability of things. So I haven't actually do a large scale reconstruction yet, but I have seen some really good results. So probably, I mean, if you see some people post some really good result, maybe it is very difficult to reproduce the same result. Sometimes you see a good result, but if you do it on your own video, on your own camera, you are not getting a good result. So back then, when I tried the Gaussian splatting, and I have to do a little tweaks or adjustment here and there, and have some tips about how to take the surrounding pictures. So I get some ideas of how to get a good training source for if you want to get a really good Gaussian splatting result. But I think those things may not apply to current models, because I think the advance is quite well. But I'm not sure. Like I said, I haven't tried by myself for like one year or two. So this is just, I already see a lot of people demonstrate their works and their results. So I presume they are getting easier nowadays. And that, just like I said, I haven't tried it before. But basically, you need to, I mean, if you want to have a good reconstruction, you are going to have pretty much evenly distributed angles to these things. Like all neural network models, they are doing pretty well in the interpolations and doing not that good for extrapolation. So if you want to have a novel camera view, this view is better to be surrounded by different angles. So this view will be pretty good. And just be careful that about the blind spot. So because this one, the Gaussian splatting does not has a pre-trained weight, so it is not doing very well on impending. It will going to be very blurred. So just if there are some potentially blind spot, you want a better quality, so go eliminate those blind spots by moving your camera to see the blind spot. But like I said, I haven't catch the advance in these 2 years. Maybe they are getting better. Okay, so why is this models has relation to the generative models? So first of all, they can be considered as a generative model because they can generate a novel view of the things. Although they are not a typical generative model, but if you imagine these kind of things are like a distribution. So we are using a new angle, then we can construct a new fields. But they are not like a generative model because their input are none. They are not latent. So in general, a typical characteristic of a generative model is there is something called latent. Like we cannot parameterize the all the conditions and all the things that can affect the result. But in the sense about the Gaussian spiraling and the nerve, for in a nerve, it has a model like a 5-dimensional, like x, y, z, and the direction. And the Gaussian spiraling is using a Gaussian spiraling as your contraction element. So you already had, although they are just approximate models, but they are something you already know. So the input is none. The input is none, not just something we have to figure out, or like a latent. So so that's the major difference between them and generative model. But on the other hand, you can generate a new a novel view of the same object. So in that sense, it's kind of sort of like generative things. But if you want to, I mean, in the mechanism or like in the difficulty or in the challenge, they are so different because one has a latent and the other doesn't have. But the thing is, we can use Gaussian spiraling or nerve as a fundamental representation if we want to do some typical generative models like text to 3D things. So one way to do that is that, okay, can we actually generate a different fields of images of the same object then by using a diffusion model? But we are telling using a text prompt, okay, front view, side view, and different view. Then we can use the 3D Gaussian spiraling to generate the 3D object. Okay, this is a way to do that. But if the image generative model is not, one way to do that is we train an image generative model so that it can is fine-tuned to generate different view, like side view, left view, right view, front view, bottom view, up view, top view, back view, like this different angle. We train a model to spatially doing this kind of tests. This is one way to do that. Another way to do that is using optimization things to, okay, because if the front view and the side view does not match, is not compatible, we cannot generate a very good 3D object. So we can use how good this 3D object or how smooth this 3D object to guide the image generation. So we are optimizing the diffusion. Actually, we are guiding the diffusion generation and the Gaussian spiraling at the same time, so that we can use one view and the front view and the side view and top view all together to generate something and make these views compatible so that they can generate some reasonable 3D object. So that is another idea. And there are also other ideas by taking some part of the 3D Gaussian spiraling things as a representation. Okay, so here is a way to use 3D text to 3D using 2D diffusion. The sense, as you can see that it uses nerve as a representation and doing the training. But that one is just an idea, and there are other ideas as well. I'm just saying that given a proof that you can combine nerve, there are some work that combine nerve with the diffusion model. This one is using the diffusion model to generate the whole thing directly. But like I said, you can start from an image to using image to generate 3D object as well. Another way, another more modern models is the triple SR, which is quite popular, I think, in last year, and it's still pretty impressive for generate like cartoonish 3D object. It also have a mesh output. I am not entirely sure it use Nerf or not, but it is a pretty good model back then. The current model that is more interesting is 混元 3D model, which has been here around like maybe like 2 months, 3 months or so. This one does not use Nerf. It uses a different presentation. It basically is a latent diffusion model. I should say first that it has 2 parts. One part is the shape for the shape generation, and the second part is to paint the texture on the shape. So the first part is more related to like 3D reconstruction. It is not using Gaussian splatting or Nerf, but it is still using some kind of like a point cloud like things to present the shape of the things. But eventually it will generate a mesh. So the first part is using a DIT to generate the shape. Then the second part is to do the painting. So to actually make it color and has texture. We are more focusing on the first part, but for the second part, there are also something interesting to see. So for the first part, it has a shape VAE. So like other things for using diffusion model, especially latent diffusion model, you can pretty much use diffusion model on anything. As long as you have encoder, autoencoder, to encode your things into latent, no matter it is an image, a video, an audio, or like a language, or like in this case, a 3D model. If you can have a variation autoencoder to make it to become a latent, you simply use the DIT, the denoising transformer, to do the denoising, to do the diffusion denoising process. That's all. But the key point is always how do you actually encode or decode the object or the things into a latent. So here they are using sampling on the mesh, like a point cloud on the mesh. But what they are emphasis is they are using a different importance on the different sample. They are using importance aware sampling to do that. But anyway, they are encoding a 3D object into a latent, and they use diffusion. For texture senses, they are doing different way, different. If they have a reference, they are getting a reference image. They are using a reference image, but you can do it in the totally text to 3D manner without any reference image. So if they have a reference image, they will think about reference image and rotate it in different things. So the interesting thing about the diffusion part is they are also designing their own DIT. They're using their own DIT, like double stream DIT, which very similar to which one? Oh, okay, Stable Diffusion 3. Stable Diffusion 3 also have by stream, double stream DIT. So this one is pretty, I would not say standard, but reasonable and not uncommon. So when you want to design your own DIT. These are all kind of building blocks that already existed, and it also can be considered as a reference if you want to design your own DIT. Also, I think the benefit of it is to expand your imagination. Sometimes you are thinking, okay, maybe this is too radical. This modification is too radical, too dangerous. But I mean, people are doing this a lot. So this one is doable. But still, you have to follow in some common sense, and it's still not easy, but this is something you should not be afraid of. 所以这边主要是说，这个其实只是它的 block 很像那个 Stable Diffusion 所以那种双流的那个 DIT。那当你需要2个流的时候，像这边 shape 和 image 的时候，它就会用2个流来做这件事情。好，这是很常见的事情。那这边当然有一些其他的一些设计啊。那我只是说这个东西就是依照你的需求，你就可以做出不同的设计。那第一个就是你可以参考别人当做你的工具项条元素。第二个事情就是，有的时候大家会觉得，我要怎么设计这个东西，好像太过激进了，能够改到这么多，会干什么？真的是不行吧？但其实，它在合理的范围，就是因为它是有道理的，所以这种合理范围这种东西本来就是可以做的。那有一些东西不会动它，就是像这三明治结构，就是那个 normalization 跟什么那个，因为那个有被调过几次，那个东西是比较没有道理的，不是说就是说你不容易直接想出来的，它是要靠实验或者经验累积的，那东西就不会去动它，因为那种结构是被证明有效的，那就不会动它。但是像这种它的流怎么跑啊那些的，那个只要那个基本结构对，就是刚才说那些需要经验的那些东西，比如说 attention 后面接什么，然后那个你要用什么样的，好，要不要用 MOE 啊什么那种，那都是基本的一些可以做的事情。但它的流怎么跑，那就是按照它基本的去做。好像这边它是 linear 再加 gate， 这个当然是比较特别一点点，就 MLP 加 gate 啊，因为它可能只是在说它的那个，就是我们之前讲那个 gate 那个东西，那个 GLU 啊那种后面加那个东西。然后像这种东西，你看到标准的嘛，就是 okay, and also can say that this one is kind of a standard way to add actual condition like scale and shift from these things into this model. So these are also standard way of injecting condition into the transformer blocks. So all of this one, so you have several choices, and other than this one, if everything feels that is aligned with common sense and reasonable to satisfy your goal, your needs, to satisfy your needs, everything is doable and makes sense. Those all make sense. Okay, and this is 3D Paint. The only thing that I want to emphasize is it follows a paradigm to separate the things, a big problem, into small piece of problem. So one of the, suppose you already has an image and you want to apply this image into a 3D model. There are several different small problems on it. So if you want to just like a UV mapping from this one to this model, I mean, suppose you already have a model and have an image. Basically, you can do a texture on it by UV mapping directly on it. But the problem is this mapping cannot be used directly as a texture. I mean, you can use it and you will get a sort of kind of okay result. And sometimes it even feels like photorealistic. But the problem is the photo you get are usually already get lighting. Like if you have a people, usually it will have some kind of directional lighting. So there will be shadow somewhere and reflections and spectacular lighting and on certain part. So certain part is going to be lighter and a certain part is going to be darker than it's supposed to be. So you need to do a process called delighting. So you can see that maybe it's called delight. Okay, no, I cannot search because this is an image. But you can see that, okay, delighting module. So you need, when you want to solve a big problem, you have to, one of the things you might want to do is to identify the small part of this problem. Like, and then you can solve them one by one, or finding existing solution to part of them. Then you focus on other part that you want to improve. So if you don't do that, just saying, okay, we'll do the 3D painting and didn't even realize there is an issue on delighting. So maybe sometimes the delighting is another issue because you already has a texture already, and this one is already delighted. Then this is not issue. But if you don't even realize this is an issue, that because we have like do like oral test on even on defense or like in other case for a candidate. This is some question that we were going to ask. Do you even realize in this process, okay, you are claiming you have done a project or research on this on these things, like applying this as a texture of these things. Even though I haven't done this seriously, but we can already know that there are several parts of challenge on this process. One of the things is delighting, because I mean, I have tried a lot of times, like using a photo and apply it directly on the models. So you can sort of have a photorealistic if the people does not move too much. You will have some kind of photorealistic mapping. And I disable all the lighting options. So I use the original lighting on the photo. But if the man is like rotate his head or change his position, if you notice carefully, you will see the shadow is unnatural. So that's the issue. So if you want to apply a photo on this kind of things, delighting is something you are going to notice, and you must do something to solve this issue. So the good answer to this question is, okay, you tell me, okay, we don't have this issue because we are using something already like diffusion generated things. They are already a texture map. Or you say that, okay, I didn't solve this one, but I used some models to solve this one. And that's also okay issue. And of course, the best one might be, okay, I have an idea and I invented an algorithm to solve this one. Okay, and this one has a best result so far. So that is also a pretty good answer. And the bad answer, the poor answer is that you answer, okay, I don't know what you're talking. I'm using a repo from GitHub and doing all the things. I don't know anything about it. So what is relating? I kind of like just give any you are just kind of like running things and without any proof or evidence you have ever working on this project. Also, I think this one you first will need. I mean, separate the things into delighting module, and to isolate the delighting process into a module is not the only way to solve it. So maybe there will be an end-to-end solution. So, but for our human beings, a way to solve it without using a genius method is like, okay, we separate into several different modules. So this is one way to do that, and this is a good way to do that, to separate the things into a huge process into small steps and solve them one by one. So this is a divide and conquer paradigm, which is a pretty common and effective. And for all text to 3D things, this one is a report I collect last year. And there are other awesome text to 3D reports. An awesome something is a curated list of something, which is getting popular like 10 years ago, since 10 years ago. So if you want to search something, some topic, one way to do that is still search awesome and your topic. And the chances are some people already curated a list about the results about this topic. So this one is an awesome text to 3D curated list. There are more than this one, but this one is updated and organized pretty well. So you can see the last update is 4 days ago. If you just scroll down, you will see it's a very short list. And one thing you can see that it's not only list the algorithm, it's list like a data set. So if you want to do things by yourself, you can already have a beginning point, start point to see the data set. This data set, some of them are quite huge. Not all of them are very usable because, in fact, they are. This is a text to 3D is a very general topic. There are many different scenarios on text to 3D. Sometimes you want to generate an object. Sometimes you want to generate a scene or maybe a building, and including the interior and the outlook of the building. So not every data set is serving the same purpose. So I have downloaded many of them, and some of them are not immediately useful to me. But it is a start point and a correction that you can look at. And also there are some framework existing. You can try of them. But most part are here in paper. Here is like X to 3D. Not only text to 3D, maybe like image to 3D. There are also like audio to 3D. Like hear someone's voice, and then it generates a picture of a guess, educated or trained guess of what these people should look like, the person should look like, and generate the animation. So here are a bunch collection of like the models that generate 3D object, including like using diffusion, like dreaming diffusion is the dreaming Gaussian. There should be a dreaming diffusion since the dreaming Gaussian seems to be using Gaussian sparking and maybe diffusion model altogether. And then the newer one, I lost the track of which one is better, but I see that the Hunyuan 3D is kind of decent, if not SOTA, 3 object detection. 3 object generating model available. I've seen this whole time because the title is pretty catchy, but I haven't seen the details in it. And also there are 3D editing and composition and avatar generation and manipulation, which is more like you can generate people, realistic or animated, cartoonish people that you can use it as an avatar, like control its motion. Also here collect a lot of things. And here are also dynamic content generation This is more like a smaller neural topic, but it can generate kind of like a more like a thing scenario, a thing that is like 4D dimension. Maybe you can. Okay. 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 Maybe I did something wrong and then make it blocked. Okay. I'll check what I did wrong here. But anyway, you can actually see. I was just trying to see the image to show you what it means. Anyway, it has a lot of resources that you can find out. Okay, so let's pretty much conclude what we are going to cover in this semester. Let me do a quick summarization in 30 seconds. We have already encountered like autoencoders and autoregressive models, including language models, and also we put a lot of time to do the like generative. We didn't cover generative adversary things, but we are covering like diffusion models a lot and like flow matching, rectify flow matching things, and how to fine tune them. And finally, we get some topics about the latest research on this on this field, like what we introduced today and last week. So I hope the material covered in this semester is useful for you. And that's all for this semester.